Subscribe to Boring Science for new videos every day. Now, let us begin. The phenomenon of tides, which has been observed by coastal inhabitants for thousands upon thousands of years, is fundamentally a consequence of the gravitational interactions between the Earth, the Moon, and the Sun. And it is through the careful and methodical examination of these gravitational forces that the predictable rise and fall of ocean waters along coastlines can be understood in considerable, and perhaps exhausting, detail. The word tide itself derives from an Old English term meaning time or season, which is fitting because the tides operate on cycles that are remarkably regular, repeating with a periodicity that has allowed mariners, fishermen, and scientists to anticipate their behavior with a degree of accuracy that improves with each passing century of observation and mathematical refinement. At its most elementary level, a tide may be defined as the periodic rise and fall of the surface of a body of water, caused primarily by the gravitational attraction exerted upon the Earth by the Moon and, to a somewhat lesser but still significant extent, by the Sun. The vertical change in water level between high tide and low tide is referred to as the tidal range, and this range varies considerably depending on geographic location, the configuration of the coastline, the depth of the ocean basin, and the relative positions of the Moon and Sun with respect to the Earth at any given moment in time. It is worth noting, in a manner that may perhaps be considered tediously thorough, that tides affect not only the oceans, but also, to a far smaller and less perceptible degree, large lakes, the atmosphere, and even the solid crust of the Earth itself. Though these latter manifestations are of such modest amplitude that they are generally imperceptible to the unaided human senses and are detected only through the use of sensitive instruments. The gravitational theory that provides the foundation for understanding tidal phenomena was articulated by Sir Isaac Newton in his monumental work Philosophiae Naturalis Principia Mathematica, published in the year 1687. Newton's law of universal gravitation states, in language that has been repeated in textbooks for more than 3 centuries, that every particle of matter in the universe attracts every other particle of matter with a force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. This relationship is expressed mathematically as F equals G times m1 times m2 divided by r squared, where F represents the gravitational force, G is the gravitational constant, which has been determined through painstaking experimental measurement to have a value of approximately 6.674 times 10 to the negative 11th power cubic meters per kilogram per second squared. M1 and M2 are the masses of the two objects in question, and r is the distance between their centers. It is this deceptively simple equation, composed of only a handful of variables, that governs the behavior of tides on a planetary scale. And it is the differential application of this force across the diameter of the Earth that gives rise to the tidal bulges observed on opposite sides of the planet. The Moon, which orbits the Earth at a mean distance of approximately 384,400 kilometers, is the primary agent responsible for the generation of tides on our planet. Despite having a mass of only about 7.342 times 10 to the 22nd power kilograms, which is roughly 1/81st of the mass of the Earth, the Moon's relative proximity to the Earth means that its gravitational influence on the oceans is substantial. The gravitational force exerted by the Moon on the near side of the Earth, that is, the side facing the Moon at any given time, is measurably stronger than the gravitational force exerted on the center of the Earth, which is in turn stronger than the force exerted on the far side of the Earth. This differential in gravitational force across the diameter of the Earth, a distance of approximately 12,742 kilometers, is what produces the tidal force, and it is this tidal force, rather than the absolute gravitational pull, that is responsible for the generation of tides. On the side of the Earth nearest to the Moon, the ocean water is pulled more strongly toward the Moon than is the solid body of the Earth beneath it, and consequently the water bulges outward in the direction of the Moon. This is perhaps the more intuitively understandable of the two tidal bulges. On the opposite side of the Earth, the side farthest from the Moon, a second tidal bulge forms, and this one requires somewhat more careful explanation. On the far side, the solid Earth is pulled more strongly toward the Moon than is the ocean water on that distant surface, because the solid Earth is closer to the Moon by one full planetary diameter. The result is that the Earth is, in effect, pulled away from the water on the far side, leaving the water to bulge outward in the direction opposite to the Moon. These two bulges, one facing the Moon and one facing away from it, are present simultaneously, and as the Earth rotates on its axis once every approximately 23 hours and 56 minutes, a given point on the coast will pass through both bulges in the course of a single rotation, experiencing 2 high tides and 2 low tides per day, or more precisely, per lunar day, which is approximately 24 hours and 50 minutes in duration, due to the Moon's own orbital motion around the Earth. The tidal force, it should be noted with appropriate precision, is not simply the gravitational force itself, but rather the difference in gravitational force between 2 points separated by some distance. The tidal force exerted by the Moon on the Earth can be expressed approximately as F tidal equals 2 gmm r divided by d cubed, where g is the gravitational constant, m is the mass of the Moon. M is the mass of the portion of the Earth being considered, r is the radius of the Earth, and d is the distance between the centers of the Earth and the Moon. The critical feature of this equation is the presence of d cubed in the denominator, which means that the tidal force decreases with the cube of the distance rather than the square. This cubic dependence on distance explains why the Moon, despite being far less massive than the Sun, exerts a stronger tidal influence on the Earth. The Sun, which has a mass of approximately 1.989 times 10 to the 30th power kilograms, is vastly more massive than the Moon by a factor of roughly 27 million. However, the Sun is also vastly more distant from the Earth, located at a mean distance of approximately 149.6 million kilometers, compared to the Moon's mean distance of 384,400 kilometers. Because the tidal force depends on the cube of the distance, the Sun's enormous mass is more than counterbalanced by its far greater distance. The result, which has been calculated with considerable precision, is that the Sun's tidal force on the Earth is approximately 46% of the Moon's tidal force. This means that while the Sun does contribute significantly to the tides, it is the Moon that dominates, producing roughly 54% of the total tidal force experienced by the Earth's oceans. To express the relative magnitudes of the lunar and solar tidal forces in more concrete terms, the tidal acceleration produced by the Moon at the Earth's surface is approximately 1.1 times 10 to the negative 7th power meters per second squared, while the corresponding tidal acceleration produced by the Sun is approximately 0.52 times 10 to the negative 7th power meters per second squared. These are extraordinarily small accelerations, amounting to approximately 1/10 millionth and 1/20 millionth, respectively, of the gravitational acceleration at the Earth's surface. Yet, it is precisely these minuscule differential forces, acting persistently and continuously over the vast surface area of the world's oceans, that are responsible for the movement of billions of metric tons of water in the form of tides. The persistence of the force, combined with the fluidity of the medium upon which it acts, ensures that even an acceleration of such negligible magnitude can produce effects of considerable and observable scale. The ratio of the lunar to solar tidal force, approximately 2.17 to 1, can be derived directly from the relevant astronomical quantities. If one takes the mass of the Moon as 7.342 times 10 to the 22nd power kilograms, the mass of the Sun as 1.989 times 10 to the 30th power kilograms, the Earth-Moon distance as 384,400 kilometers, and the Earth-Sun distance as 149,600,000 kilometers, and applies the tidal force proportionality of mass divided by distance cubed. The calculation proceeds in a straightforward manner. The mass ratio of Sun to Moon is approximately 27,068,000, while the distance ratio of Sun to Moon is approximately 389.2. The cube of the distance ratio is approximately 58,970,000. Dividing the mass ratio by the cube of the distance ratio yields approximately 0.459, confirming that the Sun's tidal force is approximately 46% of the Moon's, a result that has been verified by observation countless times since the era of Newton. The interplay between the tidal forces of the Moon and the Sun gives rise to the well-documented phenomena of spring tides and neap tides, which occur in a predictable cycle approximately twice per month. Spring tides, which have nothing whatsoever to do with the season of spring, but rather derive their name from the concept of the tide springing forth with greater vigor, occur when the Sun, Moon, and Earth are aligned in a roughly straight line, a configuration that takes place during both new moon and full moon phases. During these alignments, which are referred to as syzygies in astronomical terminology, the tidal forces of the sun and moon act in the same direction, reinforcing one another, and the result is tides with a larger than average tidal range. The high tides during spring tides are higher than average, and the low tides are lower than average, producing maximum tidal ranges that can be 20% or more greater than the mean tidal range. Neap tides, by contrast, occur when the sun and moon are positioned at right angles to one another as viewed from the Earth, a configuration that arises during the first quarter and third quarter moon phases. During neap tides, the tidal force of the sun partially cancels the tidal force of the moon, and the result is tides with a smaller than average tidal range. The high tides during neap tides are lower than average, and the low tides are higher than average, producing minimum tidal ranges that may be 20% or more less than the mean. The cycle from spring tide to neap tide and back to spring tide takes approximately 14.76 days, which is half of the synodic month of approximately 29.53 days, the period of the moon's phases as observed from the Earth. There are additional factors that modulate the tidal force over longer timescales, and these are worth enumerating even at the risk of excessive thoroughness. The moon's orbit around the Earth is not perfectly circular, but rather elliptical, with an eccentricity of approximately 0.0549. When the moon is at perigee, its closest approach to the Earth at a distance of approximately 363,300 kilometers, the tidal force is measurably stronger than when the moon is at apogee, its farthest point at a distance of approximately 405,500 kilometers. The difference in tidal force between perigee and apogee can be as much as approximately 48%, owing to the cubic dependence of tidal force on distance. Similarly, the Earth's orbit around the Sun is slightly elliptical, with an eccentricity of approximately 0.0167, and the Sun's tidal force is correspondingly slightly greater in early January. When the Earth is at perihelion at a distance of approximately 147.1 million kilometers, than in early July, when it is at aphelion at approximately 152.1 million kilometers. Though this variation is considerably smaller than the lunar variation. The declination of the moon, which is its angular position north or south of the Earth's equatorial plane, also affects the tides. The moon's orbit is inclined at approximately 5.145 degrees to the plane of the Earth's orbit around the Sun, and because the Earth's equatorial plane is tilted at approximately 23.44 degrees to the orbital plane, the moon's declination varies over the course of a month, ranging from approximately 18.3 degrees to approximately 28.6 degrees north or south of the equator over the 18.61-year cycle of the lunar nodes. When the moon is at maximum declination, the two tidal bulges are asymmetrically positioned with respect to the equator, and this can produce tidal inequalities, in which the two high tides and two low tides in a single day are of unequal height, a phenomenon known as the diurnal inequality. The tidal force equation, when expressed in its most general vectorial form, describes a force field that varies from point to point across the surface and interior of the Earth. At any point on the Earth's surface, the tidal acceleration, which is the tidal force per unit mass, can be decomposed into horizontal and vertical components. The vertical component, directed radially outward or inward, is extremely small and is overwhelmed by the Earth's own gravitational acceleration of approximately 9.81 meters per second squared. It is the horizontal component of the tidal acceleration that is primarily responsible for moving ocean water, because this component acts tangentially to the Earth's surface and is unopposed by the much larger radial gravitational force. The maximum horizontal tidal acceleration due to the Moon is approximately 1.1 times 10 to the negative 7th power meters per second squared, which is a vanishingly small quantity, yet it acts over the vast expanse of the ocean basins. And because water is a fluid and responds readily to sustained forces, this tiny acceleration is sufficient to produce the tidal displacements of several meters that are commonly observed. It is perhaps worth reflecting at this point in the discussion on the remarkable fact that the tides, which involve the movement of trillions of metric tons of ocean water over distances of meters to tens of meters, twice daily, across the entire surface of the planet, are driven by an acceleration that is less than 100 millionth of the gravitational acceleration at the Earth's surface. This is a testament to the cumulative power of a small but persistent force acting on a fluid medium over a large spatial extent, and it illustrates a principle that recurs throughout physics, namely that large-scale phenomena can arise from the integration of individually insignificant contributions. The energy dissipated by the tides globally is estimated at approximately 3.7 terawatts, or 3.7 times 10 to the 12th power watts, of which roughly 2.5 terawatts is dissipated in the deep ocean through internal tides and turbulence, and the remaining 1.2 terawatts is dissipated in shallow coastal waters through bottom friction. The gravitational constant g, which appears in Newton's law of universal gravitation and consequently in the tidal force equation, has been the subject of experimental determination since the late 18th century, when Henry Cavendish performed his celebrated torsion balance experiment in 1798. Cavendish's original result, expressed in modern units, yielded a value of approximately 6.74 times 10 to the negative 11th power cubic meters per kilogram per second squared, which is remarkably close to the currently accepted value of 6.674 times 10 to the negative 11th power. The precision with which g is known remains relatively poor compared to other fundamental physical constants, with a relative uncertainty of approximately 2.2 times 10 to the negative 5th power. And this uncertainty propagates into calculations involving gravitational forces, including tidal forces, though the effect on practical tidal prediction is negligible because tidal predictions are based on empirical harmonic constants rather than on ab initio gravitational calculations. The Earth body tide, which is the deformation of the solid Earth itself under the influence of tidal forces, deserves mention as a phenomenon that is distinct from but related to the ocean tide. The solid Earth is not perfectly rigid, but rather deforms elastically in response to the tidal forces of the moon and sun. And this deformation produces a vertical displacement of the Earth's surface that has a maximum amplitude of approximately 30 to 40 centimeters at the equator during spring tides. The Earth body tide is described by a set of dimensionless quantities called love numbers, named after the British mathematician Augustus Edward Hopf Love, who introduced them in 1909. The principal love numbers for the Earth are H2, which describes the vertical displacement and has a value of approximately 0.609, K2, which describes the change in gravitational potential and has a value of approximately 0.302, and L2, which describes the horizontal displacement and has a value of approximately 0.0840. These numbers characterize the Earth's elastic response to tidal forcing and are of considerable importance in geodesy, geophysics, and the precise reduction of satellite altimetry data for ocean tidal studies. The atmospheric tide, though it contributes negligibly to the rise and fall of ocean water, is another manifestation of tidal forcing that is worth noting for completeness. The atmosphere responds to tidal forces in much the same way as the ocean, forming bulges of slightly higher atmospheric pressure on the sides of the Earth facing toward and away from the Moon and Sunday. However, the gravitational atmospheric tide is extremely weak, and the dominant tidal signal in atmospheric pressure is actually the solar thermal tide, which is driven by the daily heating and cooling of the atmosphere by the sun rather than by gravitational forces. The solar thermal tide produces a semi-diurnal oscillation in surface atmospheric pressure with an amplitude of approximately 1.0 to 1.5 hectopascals at tropical latitudes, which is detectable in barometric records, but has no significant effect on ocean tides. The interaction between Earth body tides and ocean tides produces a phenomenon known as tidal loading, in which the weight of the ocean tidal bulge depresses the ocean floor beneath it and produces measurable tilts and strains in the Earth's crust at distances of hundreds of kilometers from the coast. Tidal loading effects must be accounted for in the precise determination of tidal constants from coastal tide gauge records, and they are also of importance in the interpretation of geodetic measurements, gravity observations, and measurements of crustal strain and tilt. The computation of ocean tidal loading requires knowledge of the global distribution of ocean tides, the elastic properties of the Earth, and the geometry of the coastlines. And it is typically performed using Green's function methods that integrate the contribution of each element of the ocean tidal load over the entire ocean surface. The concept of the equilibrium tide, first proposed by Newton, imagines a simplified Earth entirely covered by a deep ocean, with no continents to obstruct the flow of water. In this idealized scenario, the ocean surface would adjust instantaneously to the tidal forces, forming two symmetric bulges aligned with the Moon. And the tidal range would be approximately 54 centimeters due to the Moon alone and approximately 25 centimeters due to the Sun alone, for a combined maximum of approximately 79 centimeters during spring tides. The actual tides observed on the real Earth bear only a passing resemblance to this equilibrium prediction, because the continents divide the ocean into distinct basins. The ocean depth varies enormously from place to place. The Coriolis force due to the Earth's rotation deflects the tidal flow, and the resonant properties of individual ocean basins amplify or diminish the tidal response. Nevertheless, the equilibrium tide theory provides a useful conceptual foundation upon which more realistic dynamic tide theories have been constructed, and it correctly predicts the fundamental periodicities and the relative importance of the lunar and solar contributions to the tides. The study of tides is, it must be acknowledged, a subject of almost limitless detail, and what has been presented thus far represents only the most foundational principles. The gravitational interactions are well understood, the mathematical framework is robust, and the fundamental periodicities have been catalogued with a precision that borders on the tedious. As the Earth continues its slow rotation beneath the tidal bulges raised by the Moon and Sun, the waters of the ocean respond with a regularity that has been a source of both practical utility and, for those so inclined, a gentle and persistent invitation to drowsiness, particularly when the subject is discussed at the deliberate and unhurried pace that the material so naturally invites. The classification of tidal patterns into distinct types is a matter that has occupied oceanographers for a considerable period of time, and the system that has emerged from their collective efforts divides the tides observed at various coastal locations around the world into three principal categories, each defined by the number and relative magnitude of high and low tides occurring within a single lunar day of approximately 24 hours and 50 minutes. These categories are the semi-diurnal tide, the diurnal tide, and the mixed tide, and each arises from the particular combination of astronomical forcing and local oceanographic conditions that prevails at a given location. The distinctions between these categories, while perhaps not the most riveting subject matter for general conversation, are of considerable importance to navigation, coastal engineering, and the prediction of water levels for practical purposes. The semi-diurnal tide is characterized by two high tides and two low tides of approximately equal magnitude occurring in each lunar day. This is the pattern that most closely resembles the idealized equilibrium tide predicted by Newton's theory, in which the two tidal bulges on opposite sides of the Earth produce two cycles of rise and fall as the Earth rotates. Semi-diurnal tides are predominant along the Atlantic coasts of Europe and Africa, along the eastern coast of South America, and along portions of the eastern coast of North America. At locations experiencing semi-diurnal tides, the period between successive high tides is approximately 12 hours and 25 minutes, and the tidal range, while varying with the spring neap cycle, tends to be relatively consistent from one tidal cycle to the next within a single day. The dominance of the semi-diurnal pattern in the Atlantic Ocean is related to the dimensions and resonant properties of the Atlantic Basin, which respond preferentially to the semi-diurnal forcing frequencies. The diurnal tide, by contrast, is characterized by only one high tide and one low tide per lunar day, with a period of approximately 24 hours and 50 minutes between successive high tides. Diurnal tides are less common than semi-diurnal tides on a global scale, but they are observed at certain locations, particularly in the Gulf of Mexico, along portions of the coast of Southeast Asia, and in some parts of the Pacific Ocean. The occurrence of diurnal tides is associated with locations where the semi-diurnal tidal constituents are suppressed by the local geometry of the basin or coastline, allowing the diurnal constituents, which arise primarily from the declination of the moon and sun relative to the equator, to dominate. At locations such as Pensacola, Florida, and Dusan, Vietnam, the tidal pattern is predominantly diurnal for much of the month, with a single daily high tide and low tide being clearly distinguishable. The mixed tide, which is sometimes further subdivided into mixed predominantly semi-diurnal and mixed predominantly diurnal categories, exhibits characteristics of both semi-diurnal and diurnal patterns. At locations experiencing mixed tides, 2 high tides and 2 low tides typically occur per lunar day, but the successive high tides and low tides are of markedly unequal height, a condition referred to as diurnal inequality. During portions of the month when the moon's declination is near zero, the mixed tide may appear nearly semi-diurnal, with the 2 daily high tides being of similar magnitude. When the moon's declination is at its maximum, however, the diurnal inequality becomes pronounced, and the pattern may approach a diurnal character, with one of the 2 daily high tides being so reduced in amplitude as to be barely perceptible. Mixed tides are widespread along the Pacific coast of North America, from Alaska to California, and are also observed along the coasts of Australia, India, and many Pacific islands. The tidal range, which is the vertical difference between the water level at high tide and the water level at the subsequent low tide, varies enormously from one location to another around the world. And this variation is a subject that can be explored at considerable length without exhausting the available data. In the open ocean, far from the influence of coastlines and shallow water, the tidal range is typically quite modest, on the order of 0.5 to 1.0 meters. Near coastlines, however, the tidal range can be amplified dramatically by a variety of mechanisms, including the funneling of tidal currents into narrow channels and bays, the shoaling of water as the continental shelf is approached, and the resonant amplification of the tide in basins whose natural period of oscillation is close to the tidal period. The most extreme tidal range in the world is observed in the Bay of Fundy, located between the Canadian provinces of New Brunswick and Nova Scotia on the eastern coast of North America. At Burncoat Head, Nova Scotia, the mean spring tidal range has been measured at approximately 14.5 meters, and the maximum recorded tidal range is approximately 16.3 meters, a figure that is sometimes quoted as 16.8 meters, depending on the source and the specific measurement conditions. The extraordinary tidal range in the Bay of Fundy is attributed to the near-resonant condition of the bay, which has a natural period of oscillation of approximately 13 hours, sufficiently close to the semi-diurnal tidal period of 12 hours and 25 minutes that the tidal response is greatly amplified. The bay's funnel-shaped geometry, with its length of approximately 270 kilometers and its progressive narrowing and shallowing toward the head, further concentrates the tidal energy and increases the range. It has been estimated that approximately 100 billion metric tons of water flow in and out of the Bay of Fundy with each tide, a volume that exceeds the combined flow of all the world's freshwater rivers. Other locations with notably large tidal ranges include the Severn Estuary in the United Kingdom, where spring tidal ranges of approximately 14.5 meters have been recorded at certain points, and Ungava Bay in northern Quebec, Canada, where tidal ranges exceeding 16 meters have been measured, leading to an ongoing and not particularly exciting debate about which location can rightfully claim the title of having the world's largest tidal range. The Bristol Channel, the Wash on the east coast of England, the Gulf of St. Malo on the coast of Brittany in France, and Cook Inlet in Alaska are all locations where tidal ranges regularly exceed 9 meters during spring tides. At the other extreme, locations such as the Mediterranean Sea, the Baltic Sea, and certain mid-ocean islands experience tidal ranges of less than 0.5 meters, and in some enclosed or semi-enclosed basins, the tides are so small as to be practically negligible. The concept of amphidromic points is central to the understanding of how tides propagate through ocean basins, and it is a concept that, while somewhat abstract, can be explained with sufficient patience and deliberation. An amphidromic point is a location in the ocean where the tidal range is zero, meaning that the water level at that point does not rise or fall with the tide. The tidal wave, which in this context refers not to a tsunami, but to the long-period wave associated with the tide, rotates around the amphidromic point, with the crest of the wave sweeping around the point in a circular or elliptical pattern over the course of one tidal cycle. The direction of rotation is generally counterclockwise in the northern hemisphere and clockwise in the southern hemisphere, a consequence of the Coriolis effect, which deflects moving fluids to the right in the northern hemisphere and to the left in the southern hemisphere. Lines connecting points that experience high tide at the same time are called cotidal lines, and these lines radiate outward from each amphidromic point like the spokes of a wheel. The tidal range increases with distance from the amphidromic point, so that locations far from the point experience larger tides than locations near it. The pattern of amphidromic points and cotidal lines in a particular ocean basin is determined by the basin's geometry, depth, and the strength of the Coriolis effect at that latitude. In the North Atlantic Ocean, there are several amphidromic points for the principal semi-diurnal tide, and the cotidal lines radiating from these points explain why different locations along the Atlantic coast experience high tide at different times of day, even though they are all responding to the same astronomical forcing. The detailed mapping of amphidromic systems was first accomplished in the early 20th century through the analysis of tidal observations from coastal stations. and it has been subsequently refined through satellite altimetry measurements and numerical ocean models. The mathematical description of tides relies heavily on the method of harmonic analysis, a technique that was developed in its application to tides primarily by Sir William Thomson, later Lord Kelvin, and Sir George Howard Darwin, the son of Charles Darwin, during the latter half of the 19th century. In harmonic analysis, the observed tide at any location is represented as the sum of a large number of sinusoidal components, each with a specific period, amplitude, and phase. These components are called tidal constituents, and each one corresponds to a particular aspect of the astronomical forcing. The number of tidal constituents that have been identified and catalogued is remarkably large, exceeding 600 in some comprehensive listings, though in practice a much smaller number suffices for most prediction purposes. The most important tidal constituent is designated M2, which represents the principal lunar semi-diurnal tide with a period of 12 hours, 25 minutes, and 14 seconds. This constituent arises from the gravitational attraction of the Moon and is the dominant component of the tide at most locations worldwide. The second most important constituent is S2, the principal solar semi-diurnal tide, with a period of exactly 12 hours, which arises from the gravitational attraction of the Sun. The ratio of the amplitude of S2 to M2 at a particular location determines the relative importance of the spring-neap cycle at that location. Other significant semi-diurnal constituents include N2, the larger lunar elliptic semi-diurnal constituent with a period of 12 hours, 39 minutes, and 30 seconds, which accounts for the variation in tidal force due to the eccentricity of the Moon's orbit, and K2, the lunisolar semi-diurnal constituent with a period of 11 hours, 58 minutes, and 2 seconds, which accounts for changes in the declination of the Sun and Moon. Among the diurnal constituents, the most important are K1, the lunisolar diurnal constituent with a period of 23 hours, 56 minutes, and 4 seconds, and O1. The principal lunar diurnal constituent with a period of 25 hours, 49 minutes, and 10 seconds. These diurnal constituents are primarily responsible for the diurnal inequality observed in mixed tides and for the purely diurnal tides found at certain locations. The constituent P1, the principal solar diurnal constituent with a period of 24 hours, 3 minutes, and 57 seconds, and the constituent Q1, the larger lunar elliptic diurnal constituent with a period of 26 hours, 52 minutes, and 6 seconds, are also of considerable importance in tidal analysis. The process of harmonic analysis involves fitting the observed tidal record at a particular location to a mathematical model consisting of the sum of these sinusoidal constituents. By analyzing a sufficiently long record of water level measurements, typically at least 1 year of hourly observations, the amplitude and phase of each constituent can be determined with reasonable accuracy. Once these harmonic constants have been established for a particular location, they can be used to predict the tide at that location for any future date, simply by computing the sum of all the constituents at the desired time, using the known astronomical arguments that determine the phase of each constituent. This method of tidal prediction is remarkably accurate, typically achieving errors of only a few centimeters at locations where good harmonic constants are available. And it remains the standard method used by national hydrographic offices around the world for the production of official tide tables. The equilibrium tide theory, as previously mentioned, assumes that the ocean surface responds instantaneously to the tidal forces and adopts the shape of an equipotential surface of the combined gravitational and centrifugal forces. While this theory correctly identifies the fundamental forcing frequencies and provides a useful first approximation, it fails to account for many features of the observed tides, particularly the large amplification of the tide in certain basins and the complex phase relationships between the forcing and the response. The dynamic tide theory, developed principally by Pierre-Simon Laplace in the late 18th century and refined by many subsequent investigators, treats the tides as long waves propagating through ocean basins of finite depth, subject to the Coriolis force and constrained by continental boundaries. In Laplace's dynamic theory, the tidal equations, now known as the Laplace tidal equations, describe the horizontal motion of water under the combined influence of the tidal forcing, the pressure gradient due to the slope of the sea surface, the Coriolis force, and frictional effects. These equations, which are a form of the shallow water equations with an added forcing term, are partial differential equations that can be solved numerically for realistic ocean geometries and bathymetry. The solutions reveal the amphidromic systems described earlier, and they demonstrate how the natural resonances of ocean basins can amplify or suppress particular tidal constituents. The success of dynamic tide theory in reproducing the observed global pattern of tides, including the distribution of amphidromic points and the variation of tidal range from place to place, represents one of the notable achievements of classical physical oceanography. The distinction between the equilibrium and dynamic approaches to tidal theory is analogous, in a sense, to the distinction between statics and dynamics in mechanics more broadly. The equilibrium theory asks what shape the ocean surface would assume if it could reach a state of static balance with the applied forces, while the dynamic theory recognizes that the ocean is a fluid medium through which waves propagate at finite speeds, and that the response of the ocean to tidal forcing is fundamentally a wave phenomenon, subject to all the complexities of wave propagation, reflection, refraction, and resonance. It is the dynamic theory that explains why the tidal range in the Bay of Fundy is so extraordinarily large, why the tide in the Mediterranean is so small, and why the pattern of tides varies so dramatically from one coastline to another, even at locations separated by relatively short distances. The detailed numerical modeling of tides in modern oceanography employs computational techniques that would have been unimaginable to Laplace and Kelvin, involving the solution of the tidal equations on grids with spatial resolutions of a few kilometers or less, incorporating realistic bathymetry derived from sonar surveys and satellite altimetry. and including parameterizations of bottom friction, turbulent dissipation, and the loading and self-attraction of the ocean on the solid Earth. These models, such as the FES finite element solution series developed by French oceanographers and the TPXO series developed at Oregon State University, provide global tidal predictions with centimeter-level accuracy in the deep ocean and somewhat reduced accuracy in shallow coastal waters where local effects become dominant. The continuous improvement of these models, driven by the availability of ever more precise satellite observations and ever more powerful computational resources, is a process that proceeds with the steady, methodical, and fundamentally unhurried character that is so admirably suited to the present context. The long-period tidal constituents, which have periods ranging from approximately 13.66 days to 18.61 years, are also worth mentioning, if only for the sake of completeness. The fortnightly constituent, designated MF, with a period of 13.66 days, arises from the variation in the Moon's declination over the course of its orbit. The monthly constituent, designated MM, with a period of 27.55 days, arises from the variation in the Moon's distance due to the eccentricity of its orbit. The semiannual constituent, designated SSA, with a period of 182.62 days, arises from the variation in the Sun's declination over the course of the year. And the nodal modulation, with a period of 18.61 years, arises from the regression of the lunar nodes, the points where the Moon's orbit crosses the plane of the Earth's orbit. These long-period tides have very small amplitudes in the ocean, typically a few centimeters at most, but they are of interest in geodesy, geophysics, and the study of the Earth's elastic response to tidal loading. And their inclusion in tidal predictions contributes to the overall accuracy of the predictions over long time spans. The form number, or form factor, designated F, is a dimensionless quantity used to classify the type of tide at a particular location, and it is defined as the ratio of the sum of the amplitudes of the two principal diurnal constituents K1 and O1 to the sum of the amplitudes of the two principal semidiurnal constituents M2 and S2. That is, F equals the quantity K1 plus O1 divided by the quantity M2 plus S2. When F is less than 0.25, the tide is classified as semidiurnal. When F is between 0.25 and 1.5, the tide is classified as mixed, predominantly semidiurnal. When F is between 1.5 and 3.0, the tide is classified as mixed, predominantly diurnal. And when F exceeds 3.0, the tide is classified as diurnal. This classification scheme, while somewhat arbitrary in its boundary values, provides a convenient and widely used method for characterizing the tidal regime at any location where the principal harmonic constants are known. The shallow water tidal constituents, which arise from the nonlinear interaction of the deep water tidal constituents as the tidal wave propagates into shallow coastal waters, add a further layer of complexity to the harmonic analysis of tides. In shallow water, The tidal wave becomes distorted because the crest of the wave, where the water is deepest, travels faster than the trough, where the water is shallowest. This distortion generates harmonic overtones and compound tides with frequencies that are sums and differences of the frequencies of the deep water constituents. The most important shallow water constituents include M4, with a period of 6 hours, 12 minutes, and 37 seconds, which is the first overtide of M2, M6, with a period of 4 hours, 8 minutes, and 25 seconds, which is the second overtide of M2 and MS4, with a period of 6 hours, 5 minutes, and 27 seconds, which arises from the nonlinear interaction of M2 and S2. These shallow water constituents can have significant amplitudes in estuaries and on continental shelves, and their inclusion in harmonic analysis is essential for accurate tidal prediction at coastal locations. The nodal modulation of tidal constituents is a long-period variation with a period of 18.61 years that arises from the regression of the lunar nodes, the points where the Moon's orbit intersects the plane of the Earth's orbit around the Sun. The lunar nodes complete one full revolution around the Earth's orbit in 18.61 years, and during this cycle, the maximum declination of the Moon varies between approximately 18.3 degrees and 28.6 degrees. This variation affects the amplitudes and phases of certain tidal constituents, particularly the diurnal constituents K1 and O1, which can vary in amplitude by approximately 11% and 19% respectively over the nodal cycle. The semi-diurnal constituent M2 varies in amplitude by approximately 3.7% over the same cycle. These nodal corrections must be applied to the harmonic constants when making tidal predictions, and they are computed from the longitude of the ascending lunar node using established astronomical formulas. The current nodal cycle began with a minimum lunar declination in 2015 and will reach its maximum in approximately 2025, after which it will decline again toward a minimum in approximately 2034. The radiational tidal constituents, which arise not from gravitational forces, but from the periodic heating of the ocean surface and atmosphere by solar radiation, are sometimes included in harmonic analysis of tides, although they are not true gravitational tides in the strict sense. The most important radiational constituent is S1, with a period of 24 hours, which arises from the diurnal cycle of solar heating and the associated generation of sea breezes, atmospheric pressure variations, and surface water temperature changes. The amplitude of S1 is typically small, on the order of a few millimeters to a few centimeters, but it can be significant at certain locations, particularly in enclosed or semi-enclosed basins where the meteorological forcing is amplified by the basin geometry. The constituent S2, while primarily a gravitational tide driven by the Sun's tidal force, also includes a radiational component that arises from the semi-diurnal cycle of atmospheric heating. And disentangling the gravitational and radiational contributions to S2 is a matter that has occupied the attention of tidal analysts for many decades. The subject of tidal constituents and harmonic analysis, with its catalogs of periods specified to the second, its amplitude ratios, and its phase angles, is one that can be pursued to almost arbitrary depth. And there are entire volumes devoted to the tabulation and discussion of these quantities. For the present purposes, it is sufficient to note that the method works, that it has been validated by more than a century of successful tidal prediction, and that the physical basis for the method lies in the fact that the astronomical motions that drive the tides are themselves periodic and predictable, decomposable into a finite number of harmonic components with known frequencies. The tide at any location is simply the ocean's response to this harmonic forcing, filtered and modified by the geometry and dynamics of the particular ocean basin in which the location is situated. And it is this filtering and modification that gives each coastal location its own distinctive tidal fingerprint, as unique and as monotonously regular as the tidal forcing itself. The movement of water associated with the rise and fall of the tides gives rise to tidal currents, which are the horizontal flows of water that accompany the vertical changes in water level. These currents, which can be quite strong in narrow channels, straits, and the mouths of estuaries, are of considerable practical importance to navigation, as they can assist or impede the progress of vessels and can create hazardous conditions for small craft and even for large ships in certain locations. The velocity of tidal currents varies greatly from place to place, ranging from negligible in the open ocean to several meters per second in confined waterways. In the Narrows of New York Harbor, for example, tidal currents can reach velocities of approximately 2.0 meters per second during spring tides, while in the Pentland Firth between mainland Scotland and the Orkney Islands, tidal currents exceeding 5.0 meters per second have been recorded, making it one of the most energetic tidal current sites in the world. Tidal currents are generally classified as either flood currents or ebb currents. A flood current is the flow of water in the direction of rising tide, that is, the inward flow toward the shore or up an estuary as the tide rises. An ebb current is the flow of water in the direction of falling tide, that is, the outward flow away from the shore or down an estuary as the tide falls. Between the flood and ebb phases, there are brief periods during which the current velocity is approximately zero, and these periods are referred to as slack water. The timing of slack water does not necessarily coincide exactly with the moment of high tide or low tide, because there is often a lag between the change in water level and the reversal of the current, particularly in locations where the tidal flow must traverse significant distances through channels and over shallow banks. In the open ocean, far from the influence of coastlines, tidal currents are rotary rather than rectilinear. That is, instead of flowing back and forth along a fixed axis, the current vector rotates continuously, tracing out an ellipse over the course of one tidal cycle. The orientation, eccentricity, and sense of rotation of the tidal current ellipse at any given location are determined by the local bathymetry, the latitude, and the relative contributions of the various tidal constituents. Near amphidromic points, where the tidal range is 0, the tidal currents may be particularly strong. Because the energy of the rotating tidal wave is concentrated in the kinetic energy of the current rather than in the potential energy of the water level displacement. One of the more dramatic manifestations of tidal currents is the tidal bore, a phenomenon in which the incoming tide forms a wave or series of waves that propagates upstream along a river or estuary, against the normal direction of river flow. Tidal bores occur in a relatively small number of rivers worldwide, and they require a specific combination of conditions, including a large tidal range, a funnel-shaped estuary that concentrates the incoming tidal energy, a shallow and gradually sloping river channel, and a river flow that is sufficiently modest that it can be overcome by the incoming tide. When these conditions are met, the leading edge of the incoming tide steepens into a wave front that can range from a barely perceptible undulation to a wall of water several meters high, depending on the specific location and the state of the tide. The Severn Estuary in the United Kingdom is home to one of the most well-known tidal bores in Europe, the Severn Bore, which forms on the River Severn as the tide advances up the Bristol Channel and into the narrowing estuary. The Severn Bore can reach heights of approximately 2 meters during the largest spring tides and travels upstream at velocities of approximately 13 to 21 kilometers per hour. The bore has been the subject of scientific study since at least the 19th century and has attracted recreational surfers who ride the wave for distances of several kilometers, though the scientific and recreational aspects of the phenomenon are, for present purposes, of equal and limited interest. The Qianding River in Zhejiang Province, China, produces what is widely regarded as the largest tidal bore in the world. The Qianding Bore, known locally as the Silver Dragon, can reach heights of approximately 9 meters and travel upstream at velocities of up to approximately 40 kilometers per hour. The bore forms as the tidal surge from Hangzhou Bay, which has a funnel-shaped geometry and a large tidal range of approximately 8.9 meters at its mouth, is compressed and amplified as it enters the increasingly narrow Qianding River. The phenomenon has been documented in Chinese literature for over 2,000 years, with records of organized bore-watching events dating back to at least the 2nd century BC. The energy carried by the Qianding Bore is considerable, and its passage generates noise that can reportedly be heard from a distance of several kilometers, though the precise decibel level at various distances does not appear to have been systematically measured. The Amazon River in South America experiences a tidal bore known as the Pororoca, from a Tupi word meaning great roar, which forms as the Atlantic tidal surge enters the wide mouth of the Amazon and propagates upstream through the shallow channels and islands of the river's delta. The Pororoca can reach heights of approximately 4 meters and travel upstream for distances of hundreds of kilometers at velocities of approximately 25 to 30 kilometers per hour. The bore is most pronounced during the spring tides that coincide with the March and September equinoxes, when the alignment of the sun and moon produces the largest tidal ranges. Other notable tidal bores around the world include the Petit Kodiak River Bore in New Brunswick, Canada, the Hooghly Bore on the Ganges River in India, the Dordogne bore in France, and the Batang Lupar bore in Sarawak, Malaysia. Each of these bores has its own particular characteristics, determined by the local geography, tidal range, and river conditions, and each has been the subject of varying degrees of scientific investigation and local cultural significance. The interaction between tides and coastlines produces a range of geomorphological effects that are observable over timescales ranging from individual tidal cycles to millennia. Tidal currents are significant agents of coastal erosion and sediment transport, particularly in estuaries, tidal inlets, and along open coastlines with large tidal ranges. During the flood phase of the tide, currents carry sediment landward, depositing material on tidal flats, in salt marshes, and along the shores of estuaries. During the ebb phase, currents carry sediment seaward, eroding previously deposited material and transporting it toward the open ocean. The net direction and magnitude of sediment transport depend on the asymmetry of the tidal currents, with locations where the flood current is stronger than the ebb current tending to accumulate sediment, and locations where the ebb current is dominant tending to lose sediment over time. The intertidal zone, defined as the area of the shore that is alternately submerged at high tide and exposed at low tide, is one of the most dynamic and ecologically significant environments on Earth. The extent of the intertidal zone is directly related to the tidal range, and at locations with large tidal ranges, such as the Bay of Fundy, the intertidal zone can extend horizontally for kilometers across gently sloping shores. The organisms that inhabit the intertidal zone have evolved a remarkable array of adaptations to cope with the regular alternation between submersion and exposure. And the distribution of these organisms across the intertidal zone follows a characteristic pattern of vertical zonation that has been extensively studied by marine ecologists. The zonation of intertidal communities typically follows a pattern in which the uppermost region, known as the splash zone or supralittoral fringe, is wetted only by spray and the highest spring tides and is inhabited by organisms such as lichens, cyanobacteria, and small periwinkle snails that are highly tolerant of desiccation. Below this, the high intertidal zone, or upper eulittoral, is submerged for a few hours during high tide and is characterized by barnacles, limpets, and certain species of algae. The mid-intertidal zone, or middle eulittoral, experiences approximately equal periods of submersion and exposure and supports a more diverse community including mussels, various species of seaweed, sea anemones, and a variety of mobile organisms such as crabs and sea stars. The low intertidal zone, or lower eulittoral, is exposed only during the lowest tides and supports the greatest diversity of organisms, including kelp, sea urchins, sponges, and numerous species of fish and invertebrates that are less tolerant of exposure to air. This pattern of zonation is remarkably consistent across different geographic regions and different types of substrate, although the specific species involved vary from one location to another. Tidal flats, which are broad, flat, low-lying areas of sediment that are alternately flooded and exposed by the tides, are among the most extensive intertidal habitats in the world. They are found in sheltered coastal locations where fine-grained sediment, including mud, silt, and sand, accumulates under the influence of tidal currents and wave action. The Wadden Sea, which extends along the coasts of the Netherlands, Germany, and Denmark, is the largest contiguous tidal flat system in the world, covering an area of approximately 10,000 square kilometers. It was designated as a UNESCO World Heritage Site in 2009 in recognition of its outstanding ecological value, and it supports vast populations of migratory birds, benthic invertebrates, and marine mammals. The sediment dynamics of tidal flats are governed by the interaction of tidal currents, wave energy, and biological processes, including the stabilization of sediment by microbial mats and the bioturbation of sediment by burrowing organisms. Salt marshes, which develop in the upper intertidal zone at locations where fine sediment accumulates and is colonized by salt-tolerant vegetation, are another important tidal habitat. Salt marshes are found primarily in temperate and high-latitude regions, where they occupy a position between the tidal flats below and the terrestrial environment above. The vegetation of salt marshes, which includes grasses such as Spartina alterniflora in North America and Puccinellia marittima in Europe, plays a critical role in trapping sediment, stabilizing the marsh surface, and providing habitat for a wide variety of wildlife. Salt marshes also provide important ecosystem services, including the filtration of pollutants from coastal runoff, the sequestration of carbon in organic-rich marsh soils, and the protection of inland areas from storm surges and coastal flooding. It has been estimated that salt marshes sequester carbon at rates of approximately 210 grams of carbon per square meter per year, which is considerably higher than the rate of carbon sequestration in most terrestrial forests. Mangrove forests, which occupy the intertidal zone in tropical and subtropical regions, serve a function analogous to salt marshes in temperate latitudes. Mangroves are woody plants adapted to the challenging conditions of the intertidal environment, including regular submersion in salt water, anaerobic soils, and exposure to wave and current forces. The global extent of mangrove forests has been estimated at approximately 137,760 square kilometers, distributed across 118 countries and territories, with the largest areas found in Indonesia, Brazil, Nigeria, and Australia. Mangroves provide critical ecosystem services, including coastal protection from storm surges and tsunamis, nursery habitat for commercially important fish and shrimp species, and carbon sequestration at rates estimated at approximately 6 to 8 metric tons of carbon dioxide per hectare per year. The root systems of mangroves trap and stabilize sediment brought in by tidal currents, gradually building new land and extending the coastline seaward, a process that has been observed to occur at rates of several meters per decade in favorable locations. The role of tides in the formation and maintenance of tidal inlets, which are the narrow channels connecting bays, lagoons, and estuaries to the open ocean, is a subject of considerable importance in coastal geomorphology and engineering. The dimensions of a tidal inlet are determined by a dynamic equilibrium between the tidal prism, which is the volume of water that flows through the inlet between low tide and high tide, and the littoral sediment transport along the adjacent coastline, which tends to close the inlet. This relationship was first quantified empirically by O'Brien in 1931 and has since been refined through numerous studies, establishing that the cross-sectional area of a stable tidal inlet is approximately proportional to the tidal prism, with larger tidal prisms maintaining larger inlets. The ebb tidal delta, which forms on the seaward side of a tidal inlet as the outflowing ebb current deposits sediment, and the flood tidal delta, which forms on the landward side as the inflowing flood current deposits sediment, are characteristic geomorphological features associated with tidal inlets that can extend for considerable distances and that evolve continuously under the influence of tidal currents, wave action, and storms. The phenomenon of tidal asymmetry, in which the flood and ebb phases of the tide differ in duration and current velocity, has significant implications for sediment transport in estuaries and tidal channels. In many estuaries, the flood current is of shorter duration but higher velocity than the ebb current, a condition known as flood dominance, which results in a net landward transport of sediment. In other estuaries, the ebb current is of shorter duration but higher velocity, a condition known as ebb dominance, which results in a net seaward transport. The direction of tidal asymmetry is determined by the relative amplitudes and phases of the astronomical tidal constituents and the shallow water overtides, and it can be modified by changes in estuary morphology, freshwater inflow, and sea level. Understanding and predicting tidal asymmetry is essential for the management of navigation channels, the design of coastal structures, and the prediction of long-term morphological evolution of estuaries and tidal basins. The energy contained in the tides has long been recognized as a potential source of renewable power, and various schemes for harnessing tidal energy have been proposed, developed, and in some cases implemented over the centuries. The earliest tidal mills, which used the rising tide to fill a pond behind a dam, and then release the water through a water wheel as the tide fell, were in operation in Europe as early as the medieval period. With archaeological evidence of tidal mills dating back to at least the 6th century CE. Modern tidal energy generation takes two principal forms: tidal barrage systems and tidal stream generators, each with its own set of engineering challenges, environmental considerations, and economic characteristics. A tidal barrage is essentially a dam constructed across the mouth of an estuary or bay, equipped with turbines that generate electricity as water flows through them during the flood and ebb phases of the tide. The most notable example of a tidal barrage in operation is the Rance Tidal Power Station, located on the estuary of the Rance River in Brittany, France. The Rance Station, which commenced operation on November 26, 1966, has an installed capacity of 240 megawatts and generates approximately 540 gigawatt-hours of electricity per year, sufficient to supply the needs of approximately 130,000 households. The barrage spans 750 meters across the Rance estuary and incorporates 24 bulb-type turbines, each with a capacity of 10 megawatts, that can generate power during both flood and ebb tides, as well as operating as pumps to optimize the energy output. For more than 4 decades, the Rance station held the distinction of being the largest tidal power installation in the world, until it was surpassed in 2011 by the Siwa Lake Tidal Power Station in South Korea, which has an installed capacity of 254 megawatts. The Siwa Lake Station, located on the western coast of South Korea, approximately 40 kilometers southwest of Seoul, was constructed by modifying an existing seawall that had been built in 1994 for land reclamation purposes. The station utilizes 10 submerged bulb turbines, each with a capacity of 25.4 megawatts, and generates electricity only during the flood tide, when seawater flows from the Yellow Sea into Siwa Lake through the turbines. The annual energy generation of the Siwa station is approximately 552.7 gigawatt-hours. Other operational tidal barrage installations include the Annapolis Royal Generating Station in Nova Scotia, Canada, which has a capacity of 20 megawatts and has been in operation since 1984, and the Jiangxia Tidal Power Station in Zhejiang Province, China, which has a capacity of 3.2 megawatts and has been in operation since 1980. Tidal stream generators, also known as tidal current turbines, represent a more recent approach to tidal energy that does not require the construction of a barrage across an estuary. Instead, these devices are placed directly in the path of strong tidal currents, typically in narrow channels or straits, and they generate electricity in a manner analogous to wind turbines, using the kinetic energy of the flowing water to drive a rotor connected to a generator. The energy available from a tidal current is proportional to the cube of the current velocity, which means that even modest increases in current speed result in substantial increases in available power. A tidal current of 3 meters per second, for example, carries approximately 13.8 kilowatts of power per square meter of cross-sectional area, while a current of 5 meters per second carries approximately 63.8 kilowatts per square meter. The environmental impacts of tidal barrage systems have been the subject of considerable study and debate. The construction of a barrage across an estuary fundamentally alters the hydrodynamic regime of the estuary, affecting water levels, current velocities, sedimentation patterns, and water quality both upstream and downstream of the barrage. At the Rance Tidal Power Station, the construction of the barrage in the 1960s initially caused significant ecological disruption, including changes in species composition and reductions in biodiversity within the estuary. Over the subsequent decades, however, the ecosystem adapted to the altered conditions, and the Rance estuary now supports a diverse ecological community, though one that differs in composition from the pre-barrage community. The lessons learned from the Rance experience have informed the environmental assessment of proposed tidal barrage projects elsewhere, including the various proposals for a barrage across the Severn estuary in the United Kingdom, which have been studied intermittently since the 1920s and which remain a subject of ongoing discussion, with estimated costs for the largest proposals ranging from 20 to 30 billion British pounds. Several tidal stream generator projects have been developed and tested in recent years, including the Maygen project in the Pentland Firth, Scotland, which is currently the largest planned tidal stream energy project in the world. With an initial phase of 6 megawatts installed capacity using 4 turbines that began generating power in 2016 and a planned full capacity of approximately 398 megawatts. Other notable projects include the Seagen turbine, which was installed in Strangford Lough, Northern Ireland, in 2008, with a capacity of 1.2 megawatts, and the Verdant Power Roosevelt Island Tidal Energy Project in the East River of New York City, which has been in various stages of development and testing since 2002. The development of tidal stream energy is still at a relatively early stage compared to other renewable energy technologies, and significant engineering challenges remain, including the design of turbines that can withstand the harsh marine environment, the management of biofouling on submerged structures, the minimization of impacts on marine ecosystems, and the reduction of costs to levels competitive with other forms of renewable energy generation. The global potential for tidal energy generation has been estimated at approximately 1 terawatt, though only a small fraction of this is practically exploitable with current technology, given the constraints of location, environmental impact, and economic viability. The most promising sites for tidal energy development are those with strong tidal currents or large tidal ranges in relatively shallow water close to population centers and electrical grid infrastructure. Such sites are found in various locations around the world, including the British Isles, France, Canada, South Korea, China, Australia, and the Pacific Northwest of the United States. The development of tidal energy, while proceeding at a measured and unhurried pace, represents one of the more tangible ways in which the ancient phenomenon of the tides may be put to practical use in the service of modern energy needs. And it is a subject to which researchers and engineers continue to devote their attention with a diligence that is, if not exactly thrilling, at least commendably persistent. The prediction of tides has a history that stretches back many centuries, and the methods employed have evolved from simple empirical observation to sophisticated mathematical analysis and, most recently, to the use of satellite technology and computational modeling. The earliest tide tables of which reliable records survive were produced in China during the Tang Dynasty, around the 8th century CE, and in medieval Europe. Manuscripts containing predictions of high water times at London Bridge and other locations date from the 13th century. These early predictions were based on the observed correlation between the tides and the phases of the moon, and they provided approximate rather than precise information, suitable for the needs of an era when the margin of error in maritime operations was considerably more generous than it is today. The development of tidal prediction as a quantitative science began in earnest with the work of Newton, who, as previously discussed, established the gravitational theory that explains the fundamental mechanism of tidal generation, and continued with the work of Laplace, who developed the dynamic equations governing tidal motion in ocean basins. However, the practical application of these theoretical advances to the problem of predicting tides at specific locations required the development of harmonic analysis, which was accomplished primarily during the second half of the 19th century. The key figure in this development was Sir William Thomson, later Lord Kelvin, who in 1867 proposed that the tide at any location could be represented as the sum of a number of sinusoidal components with known periods, and who subsequently devised a mechanical device for computing these sums. Kelvin's tide predicting machine, the first working model of which was completed in 1873, was an analog computer of remarkable ingenuity. The machine consisted of a series of pulleys and gears, each representing a particular tidal constituent, connected by a wire to a pen that traced out the predicted tidal curve on a moving chart. The gears were designed so that each pulley oscillated with the correct period for its assigned constituent, and the amplitude and phase of each oscillation could be adjusted to match the harmonic constants determined from tidal observations at a particular location. By turning a crank, the operator could advance the machine through time, and the pen would trace out the predicted tide for days, weeks, or months into the future. The original Kelvin machine incorporated 10 tidal constituents, and later versions, including one completed in 1879 that incorporated 20 constituents, and a machine built by the United States Coast and Geodetic Survey in 1910 that incorporated 37 constituents, provided increasingly accurate predictions. These mechanical tide predictors remained in use well into the 20th century, with the last major mechanical predictor being retired by the British Admiralty in the 1960s, when electronic computers became sufficiently capable to perform the calculations more quickly and accurately. The transition from mechanical to electronic tidal prediction occurred gradually during the mid-20th century, and the fundamental method of harmonic analysis remained unchanged. Only the means of computation was modernized. Digital computers allowed the analysis of longer tidal records, the inclusion of more tidal constituents, and the rapid generation of predictions for multiple locations simultaneously. By the 1970s, national hydrographic agencies around the world had adopted electronic computation as the standard method of tide table production, and the mechanical tide predictors that had served faithfully for a century were consigned to museums, where they may be examined at leisure by those with an interest in the history of scientific instrumentation. The advent of satellite altimetry in the latter decades of the 20th century revolutionized the study of ocean tides by providing, for the first time, measurements of sea surface height over the entire ocean, including the vast expanses of the deep sea that had previously been inaccessible to tidal observation. The Topex/Poseidon satellite, launched on August 10, 1992, as a joint mission of the United States National Aeronautics and Space Administration and the French Centre National d'Etudes Spatiales, was particularly transformative. The satellite carried a radar altimeter capable of measuring the distance between the satellite and the sea surface with a precision of approximately 3.3 centimeters. And it orbited the Earth at an altitude of approximately 1,336 kilometers, with a repeat period of approximately 9.916 days, providing coverage of approximately 95% of the ice-free ocean. The data collected by Topex/Poseidon, which operated from 1992 until 2006, enabled the determination of the global distribution of tidal amplitudes and phases with unprecedented accuracy and spatial resolution. For the first time, the locations of amphidromic points in the deep ocean could be precisely determined from direct measurements rather than inferred from coastal observations and numerical models. The results confirmed many features of the global tidal pattern that had been predicted by dynamic tide theory and numerical modeling, while the process of tidal locking occurs because the tidal bulge raised on a body by its companion does not align exactly with the direction of the companion, but is carried slightly ahead or behind by the body's rotation, creating a gravitational torque that gradually slows the rotation until it matches the orbital period. The Moon achieved its current state of tidal locking relatively early in its history, within perhaps a few tens of millions of years after its formation approximately 4.5 billion years ago, because its relatively small size made it susceptible to rapid tidal dissipation. The Earth, being much more massive, is undergoing a far slower process of tidal deceleration, but the effect is nonetheless measurable. The tidal interaction between the Earth and the Moon is gradually slowing the Earth's rotation, increasing the length of the day at a rate of approximately 2.3 milliseconds per century. This rate has been confirmed through multiple independent lines of evidence, including the analysis of ancient eclipse records, which show that eclipses observed thousands of years ago occurred at times that are inconsistent with a constant rate of Earth rotation, and the precise measurement of the Earth's rotation rate using very long baseline interferometry and atomic clocks. The consequence of the Earth's rotational deceleration is that the day is getting progressively longer, and the number of days in a year is decreasing over geological time. During the Devonian period, approximately 400 million years ago, analysis of growth patterns in fossil corals has indicated that there were approximately 400 days in a year, each approximately 21.9 hours long. During the Carboniferous period, approximately 300 million years ago, the year contained approximately 385 days of approximately 22.8 hours each. This gradual lengthening of the day is accompanied by a gradual recession of the Moon from the Earth, at a current rate of approximately 3.82 centimeters per year, as measured by lunar laser ranging experiments that bounce laser beams off retroreflectors placed on the lunar surface during the Apollo missions. The recession of the Moon is a direct consequence of the conservation of angular momentum in the Earth-Moon system. As the Earth's rotation slows, angular momentum is transferred to the Moon's orbit, causing the Moon to spiral outward. The tidal forces experienced by moons and planets throughout the solar system produce a variety of effects that extend well beyond the rise and fall of ocean waters. One of the most dramatic of these effects is tidal heating, the generation of internal heat within a body through the dissipation of energy associated with tidal deformation. Tidal heating is most significant in bodies that experience large tidal forces and that are prevented from achieving a tidally locked, circular orbit by gravitational interactions with other bodies, a condition that maintains continuous tidal flexing and energy dissipation. The most striking example of tidal heating in the solar system is provided by Io, the innermost of the 4 large Galilean moons of Jupiter. Io orbits Jupiter at a mean distance of approximately 421,700 kilometers, with an orbital period of approximately 1.769 days. And it is maintained in an orbital resonance with the moons Europa and Ganymede, known as the Laplace resonance, which forces Io's orbit to maintain a significant eccentricity of approximately 0.0041. This eccentricity means that Io's distance from Jupiter varies by approximately 3,500 kilometers over the course of each orbit, and the resulting variation in tidal force causes continuous flexing of Io's interior. The heat generated by this tidal dissipation is estimated at approximately 100 trillion watts, or 100 terawatts, which is more than 25 times the total tidal dissipation rate in the Earth's oceans. This enormous heat flux makes Io the most volcanically active body in the solar system, with hundreds of active volcanoes, lava flows covering the surface, and plumes of volcanic gas and dust rising to altitudes of several hundred kilometers. Europa, the second Galilean moon of Jupiter, also experiences significant tidal heating, though to a lesser degree than Io due to its greater distance from Jupiter. Europa orbits at a mean distance of approximately 671,100 kilometers, with a period of approximately 3.551 days, and its participation in the Laplace resonance maintains an orbital eccentricity of approximately 0.009. The tidal heating of Europa is believed to be sufficient to maintain a global ocean of liquid water beneath its icy surface, a prospect that has generated considerable interest in the scientific community regarding the potential for extraterrestrial life. The depth of Europa's subsurface ocean has been estimated at approximately 60 to 150 kilometers, based on analyses of the Moon's gravitational field, its induced magnetic field, and the geology of its ice surface, which exhibits patterns of fractures and ridges consistent with a floating ice shell underlain by liquid water. The total amount of liquid water on Europa may exceed twice the volume of all of Earth's oceans combined. Ganymede, the largest moon in the solar system, and Callisto, the outermost of the 4 Galilean moons, may also possess subsurface oceans maintained at least in part by tidal heating, though the evidence is less definitive than for Europa. Enceladus, a small moon of Saturn with a diameter of only approximately 504 kilometers, has been confirmed to possess a subsurface ocean maintained by tidal heating. Based on observations by the Cassini spacecraft of water-rich plumes erupting from fractures near the Moon's south pole. The tidal heating of Enceladus is driven by its orbital eccentricity, which is maintained by a 2-to-1 orbital resonance with the Moon Dione, and the heat flux from Enceladus's south polar region has been measured at approximately 15.8 gigawatts, which is remarkably high for such a small body and which far exceeds what would be expected from radioactive decay alone. Titan, the largest moon of Saturn, with a diameter of approximately 5,150 kilometers, also experiences tidal forces from Saturn, and measurements of Titan's gravitational field by the Cassini spacecraft suggest the presence of a subsurface ocean of water, possibly mixed with ammonia, at a depth of approximately 55 to 80 kilometers beneath the surface. The tidal deformation of Titan's surface has been measured and found to be consistent with the presence of such an ocean, as a rigid solid body would not exhibit the degree of tidal flexing that has been observed. The tidal contribution to the internal heat budget of Titan is modest compared to Io or Enceladus, but it may play a role in maintaining the subsurface ocean in a liquid state over geological timescales. Beyond the Jovian and Saturnian systems, tidal effects are observed or inferred in numerous other contexts throughout the solar system. The planet Mercury is in a 3-to-2 spin-orbit resonance with the Sun, rotating 3 times on its axis for every 2 orbits around the Sun, a state that was achieved as a result of tidal interactions between Mercury and the Sun. This resonance, which was not recognized until radar observations of Mercury in 1965, revealed its true rotation period of approximately 58.646 Earth days, contrasts with the 1-to-1 spin-orbit resonance, or synchronous rotation, that characterizes the Moon's relationship with the Earth, and that was long assumed to apply to Mercury as well. The Pluto-Charon system represents an end state of tidal evolution in which both bodies are tidally locked to each other, with Pluto's rotation period, Charon's rotation period, and Charon's orbital period all being identical at approximately 6.387 Earth days, so that each body permanently presents the same face to the other. The tidal interactions between close-orbiting exoplanets and their host stars are an area of active research in contemporary astrophysics, as many of the exoplanets discovered by transit surveys and radial velocity measurements orbit their stars at distances far smaller than Mercury's distance from the Sun, and consequently experience tidal forces of enormous magnitude. The tidal circularization of orbits, the tidal spin-up or spin-down of rotation rates, and the tidal heating of planetary interiors are all processes that must be considered in the characterization of these alien worlds, and the theoretical frameworks developed to understand tides in the solar system are being extended and applied to these new and distant contexts. The tidal interactions between binary star systems provide yet another context in which the principles of tidal theory find application. In close binary systems, where the two stars orbit each other at distances comparable to their own diameters, tidal forces can distort the shapes of the stars into prolate ellipsoids, transfer angular momentum between the star's rotations and their orbital motion, circularize initially eccentric orbits, and in extreme cases, cause mass transfer from one star to the other when the tidal distortion is sufficient to exceed the Roche limit. The timescales for tidal evolution in binary star systems depend on the stellar masses, radii, orbital parameters, and the efficiency of tidal dissipation within the stellar interiors, and they range from millions to billions of years. The study of tidal effects in binary stars has contributed to the understanding of stellar structure and evolution, and it has provided constraints on the mechanisms of tidal dissipation in bodies ranging from giant gaseous planets to solar-type stars to compact remnants such as white dwarfs and neutron stars. The concept of the Roche limit, first derived by the French astronomer Édouard Roche in 1848, is intimately connected to tidal forces and sets a fundamental constraint on the closest distance at which a satellite can orbit a larger body without being torn apart by tidal forces. The Roche limit depends on the densities of the two bodies and is approximately 2.44 times the radius of the larger body for a fluid satellite of the same density as the primary. For the Earth-Moon system, the Roche limit is approximately 18,470 kilometers, well inside the Moon's current orbital distance of 384,400 kilometers, which means the Moon is in no danger of tidal disruption. However, the rings of Saturn are believed to lie within or near Saturn's Roche limit for icy bodies, and the ring particles are thought to be debris from moons or captured objects that were tidally disrupted when they ventured too close to the planet. The disruption of comet Shoemaker-Levy 9 by Jupiter's tidal forces in 1992, which broke the comet into a chain of more than 20 fragments that subsequently impacted Jupiter in July 1994, provided a dramatic contemporary example of tidal disruption in action. The measurement of tides on other planets and moons in the solar system, while considerably more challenging than the measurement of terrestrial ocean tides, has been accomplished in several cases using spacecraft observations. The tidal deformation of Mars has been measured using tracking data from orbiting spacecraft, yielding a value for the tidal love number K2 of approximately 0.169, which provides constraints on the state and composition of Mars's interior, including evidence for a partially liquid core. The tidal deformation of Mercury has been similarly measured, with K2 determined to be approximately 0.451, a value that is consistent with a large partially molten iron core. For the giant planets, tidal interactions with their moons provide information about the internal structure and dissipative properties of these bodies, and the ongoing analysis of data from missions such as Juno at Jupiter and Cassini at Saturn continues to refine our understanding of tidal processes in these complex planetary systems. Returning to the Earth and its oceans, it is worth noting that the tides play a subtle but important role in the global climate system. The mixing of ocean waters by tidal currents, particularly in the deep ocean where internal tides break and generate turbulence, is believed to contribute significantly to the meridional overturning circulation. The global pattern of deep water formation and upwelling that transports heat from the equator toward the poles. Without the mixing energy provided by the tides, the deep ocean would become more stratified and the overturning circulation would weaken, with potentially significant consequences for the distribution of heat, nutrients, and dissolved gases throughout the ocean. The approximately 3.7 terawatts of tidal energy dissipated globally, of which roughly 1 terawatt is estimated to contribute to deep ocean mixing, thus plays a role in maintaining the ocean's thermohaline circulation that is disproportionate to the relatively modest magnitude of the tidal forces themselves. The study of tides, which has occupied the attention of scientists for more than 3 centuries, continues to yield new insights and to pose new questions, though the pace of discovery is, appropriately enough, measured and deliberate rather than rapid or surprising. The fundamental physics of tidal generation is well understood. The mathematical methods of tidal analysis and prediction are mature and reliable, and the observational record, augmented by satellite measurements, is comprehensive and growing. The applications of tidal science range from the purely practical, such as the production of tide tables for navigation, to the broadly scientific, such as the use of tidal measurements to probe the internal structure of planets and moons, to the speculative, such as the assessment of tidal effects on the habitability of exoplanets in distant stellar systems. It is perhaps fitting to conclude this extended consideration of tidal patterns and gravitational forces in coastal oceanography with the observation that the tides are among the most ancient and persistent of all geophysical phenomena. They were operating billions of years before the evolution of life on Earth. They have shaped the coastlines and influenced the evolution of marine organisms throughout geological history, and they will continue to operate for billions of years into the future, long after the specific details discussed in this narration have faded from whatever form of memory, biological or otherwise, might then exist. The moon will continue to recede from the Earth, the Earth's rotation will continue to slow, and the tides will gradually diminish in amplitude as the distance between the two bodies increases. But the process is so slow that the change is imperceptible on any human timescale. The tides of today are, for all practical purposes, indistinguishable from the tides of 1,000 years ago or 1,000 years hence, and they're steady, reliable. Monotonous rhythm is as constant and as soporific as any natural phenomenon on the surface of this planet. The gravitational forces that drive the tides are among the weakest in nature when considered on the scale of individual particles, yet they are the dominant force on the largest scales, governing the motions of planets, stars, and galaxies. The tides are a local manifestation of this universal force, a daily reminder, for those who live near the coast, of the gravitational connection between the Earth, the Moon, and the Sun. The water rises and the water falls, and the cycle repeats, as it has repeated billions of times before and will repeat billions of times again, with a regularity that is at once profoundly elegant and, when described in sufficient detail, profoundly conducive to the onset of sleep, which is, after all, the stated and singular purpose of this particular narration.